Right. So, so next Thursday we will have meeting number 2, and the coverage will be chapters 5 and 6. All right. So today I will discuss conditional distributions. And we will discuss the discrete case first. And then in the next section, we will discuss the case of absolute continuity. Okay. All right. So first of all, we'll consider 2 discrete random variables, x and y. So x and y are discrete random variables. Now, for each y in R, such that the probability that random variable y is has value equal to little y, which in terms of the PMF of capital Y is positive. Okay, so for such a Y, then we define the conditional probability mass function of discrete random variable x, given that the random variable y has value little y. As here, so the notation is x given y, okay? And the argument would be x and y. All right, so the definition is here. It's actually the conditional probability of the event. So that this is the conditional probability we discussed in chapter 3. Okay? So this is the conditional probability of this event, capital X equal to little x, given the event that capital Y is equal to little y. Okay, all right. So that by that definition in chapter 3, the numerator will be the joint event. Okay, so the joint probability divided by the probability that the given event, and the reason why we can give such a definition is because the denominator is non-zero, okay, as required here. Okay, and so in terms of the joint PMF of capital X and capital Y, right, divided by the marginal PMF of capital Y. Okay, so that okay, and then we note that by the way, and for each y in R such that the given event occurs with 0 probability, okay, then we define we define that. Okay, and by our convention, that because the given event occurs with zero probability, so this is actually the unconditional probability. Okay, you know that in chapter 3, so that this is equal to, okay, and this is for, of course, I forgot to put, okay, okay, so that the conditional probability mass function is a function defined on the whole real line. Okay? So for x, or x in R, here. Okay?
So for
yes?
the marginal probability 0, how is it defined?
Oh, because in chapter 3, we define if, okay, this is by definition. We choose to define that. Okay, yeah. With this convention, that the theory of propositions we proposed in chapter 3 has a very nice looking, right? We can have well, the statement of the propositions will be simplified. We don't need to consider whether the given event occur with positive probability or zero probability. Okay, but we have noticed that chapter 3 is the base. Okay, when we consider conditional distributions, especially the discrete case. The discrete case actually, when we define the concept of conditional probability mass function, this function is in terms of conditional probabilities of an event given another event in chapter 3. Okay, so you see that's why I deliberately to say that here. So this is by definition of conditional probability. Okay. In chapter 3. Okay, so the definition here is also from, the same thing. Okay, this definition is also from the definition of conditional probabilities of an event given another event occurs, right? In chapter 3. So, okay. Any further questions? Now we make a couple of remarks. The first one, that the conditional PMF of a discrete random variable, capital X, given that the discrete random variable y has value little y, okay, that is a non-negative function. It's a non-negative and summable function on R. Summable means that this function okay, so if y is given, right, then this is a non-negative and summable function, okay, of x on R, which means that they are only countable in many x such that this function has non-zero value. And the sum of this non-zero value is finite. We don't need to take the absolute value of the value because it is already non-negative. Okay? Okay, so I believe that you already know what is a summable function, right? Okay. The second thing is that so that because it's summable, which is equal to 1, okay? So we sum over all x in R. The reason why we can do that is because this is a summable function. Okay, and we have defined what is the meaning of this sum. Okay, we just sum over all x sub i's. The x sub I, at x sub I, the conditional PMF is positive. Okay.
So even for the discrete case, y belongs to the real number.
Yeah, because if y, all right, in this case, of course, that y is the possible value of random variable capital Y, right? Okay, and in this case, this y is not a possible value because it occurs with zero probability, right? So by definition, it is just the PMF of x. And we know PMF of x is also a summable function. This function has non-zero value for only countable many x. Okay. Any other questions? Maybe I will put third one. The conditional PMF of is given that has the same properties of the PMF of a discrete random variable. Now, all right, so from the definition you can see conditional PMF is a function in terms of defined in terms of conditional probabilities. Okay, so this is an application of this concept, but for discrete random variable x and y, conditional PMF actually retains enough information, okay, to answer the conditional probability of an event involving random variable x given an event involving random variable y. Okay, so we have to illustrate that. So now, for any Borel set A in R, we observe that the conditional probability of the event x in A given the event y equal to y is here. Okay, so this is probability that okay, and this is equal to summation of A in A divided by so this is equal to okay, if the given event has positive probability. Okay, so this event, this conditional probability we encountered in chapter 3, okay, can be obtained by using the conditional PMF of random variable x given that random variable y has value equal to y. All right, sum over all A, okay, in the Borel set capital A. And when the PMF of random variable y has zero value at little y, then we have that so we know that. Okay. So this is from chapter 3. And so this is equal to okay, and we know that the probability of such an event can be obtained by sum of the PMF of X over all little a in A. And this is equal to, again, okay, again we have that. Because in this case, the conditional PMF of X given Y is just the unconditional PMF of X, okay, by our definition. So up to now, the material we discussed are from the concept of conditional probabilities in chapter 3. Okay, they are directly related to the concept of conditional probabilities of an event, given an event to occur, right? So do that. Now, for y in R, we define the conditional cumulative distribution function of X given that on the variable y has value little y, as here. So this is actually is when A is a semi-infinite interval, okay, from minus infinity up to y, but and include y. Oh, include x, sorry. All right, so this probability is just a special case here. Okay, so the velocity A we pick up is just this semi-infinite interval. Okay, so this is one. Okay, and so this is A little bit x p. Okay. And note that the conditional CDF of X given that capital Y equal to Y has the same properties of the CDF of a discrete random variables. All right, so now we write down a proposition. Okay, relate joint PMF of two discrete random variables with conditional PMF. Okay, so the joint PMF of two discrete random variables x and y, okay, has the following identity. For all x, y in R. Okay. So the identity is exact for all x, y in R. Okay? For x, y in R. All right, so we proved the first identity, okay? Because the second one is just by symmetry, okay? Now for y in R such that the PMF of random variable y has 0 value at this point, y. Then we have that we know okay. Okay, so this implies that the Pxy is 0 for all x in R. Okay, so when the marginal PMF of random variable y is 0 at little y, then with that y, then the joint PMF has 0 value for all x in R. Right? And then that the Pxy, which is 0, which is 0 times P times 0. Okay, so we establish the identity. Okay, right? So when y, for those y that this function, this marginal PMF of up to y is 0, then we establish the identity, okay, for all x in R. And for y in R, such that this function value is positive, then we have that the conditional PMF of capital X given y, capital Y equal little y is the right? This is good for all x in R. And so this implies that if we multiply the denominator on both sides, so we have again we get the same identity. So this identity is true when no matter for any y in R, no matter the value of p sub y of is 0 or is positive. Okay. Okay, so we conclude that f of xy, p, the joint PMF of x and y is equal to this product for all xy in R. Okay, and the similar argument gives us okay, so this is the end of proof. Okay, so the identity is true for all xy in R. Any questions? We discussed independence among random variables in 6.2. So now the proposition gives us another condition, necessary condition for the independence of two discrete random variables. Okay, so the independence of two discrete random variables require that the conditional PMF of discrete random variable cap x, given that the discrete random variable capital Y equal to little y. So this conditional PMF is actually a function of x and y, so it has two variables. Okay, and this function is actually a function of x only. Okay, x only. independent of y. Okay, so this identity is the identity of two real value functions on R2, on two in random for two on two variables x and y. So, okay. All right, now we show that this identity is necessary. Now for y in R such that P sub capital Y of y is 0, then we have already by definition, right? Okay. So for rows y with this property, then the identity is true for all x in R. Okay, this is just from the definition. Now, for y in R such that the marginal per PMF of random variable y is positive at this y. Then we have that. Okay, by its definition, this is. And now, because x and y are independent, a theorem in okay, so which theorem in the section 6.2, which is proposition 6.2.b. Okay. In proposition 6.2.b, which that two discrete random variables are independent if and only if their joint PMF is exactly equal to the product, okay, of their marginal PMFs, exactly, okay, for all x, y. Now we can cancel them. So this is, okay. So again, we get the, so this is true. Okay, so that we have right. So we have the, so this is the necessary condition. Now we show that this identity as the identity of two functions on the real plane R2. Okay. Now, by proposition 6.4.8 in the above, okay, we have already Pxy is equal to P okay? So this is true for all x, y in R, but apply this identity, so this is P, okay? So we have that. And so with this identity, by proposition 6.2.b, all right, the same, that the x and y are independent. And we have done. Okay? So this proposition needed proposition 6.2.b and 6.4.a. Okay? So we have that. Okay, so you can see that in this section we create a new concept of conditional probability mass functions of a discrete random variable, given that another discrete random variable, all right, has a specific value. Okay, and this new concept help us to deal with like independence of two discrete random variables, help us to compute conditional probabilities of an event involving discrete random variable x given an event involving another discrete random variable y. Okay, so they are convenient. Okay, they are convenient. All right, so this is about dependence, okay, between two random variables. Now we extend the concept to the dependence between two collections of random variables. Okay? All right, so in general, right, we consider two collections. The first collection is called X collection, consisting of n discrete random variables. And the second collection is called Y collections of discrete random variables. All right, so this X random variable, Y random variable, they are all discrete. Okay? They are all discrete. Now for Y1, so now we define the joint probability mass function. Okay, we define the joint probability mass function of x1, x2 up to xn, given that y1 equal to y1, y2 equal to y2, ym equal to yms. So it's to be the so the numerator is the joint PMF of this m plus m discrete random variables divided by the marginal joint PMF of y random variables. Okay, if if the denominator is positive. Okay? And found it to be to the unconditional joint PMF of x1, x2 up to xn. If okay, for x1 okay, so we can look at two collections, right? And the previous case, just a special case of this definition, when each collection consisted of only one discrete random variable. Right, and the usage of the conditional. Oh, I'm sorry, I forgot a keyword. The conditional joint PMF. I'm sorry, I forgot the keywords here. Okay, so this is the conditional. All right. Now the conditional joint PMF of x sub i's, given that y sub i's has a specific values, x here. So for any Borel sets A1, A2, up to AN in R, the conditional probability of the event x1 in A1, x2 in A2, up to x sub n in AN. Okay, so this is the joint event. Given the event y1 is equal to little y1, y2 little y2, up to capital Ym equal to little ym. Okay, so we can compute. Now I will demonstrate that to compute such a conditional probability can be expressed by the conditional joint PMF of the x random variable, given that the specific information about the random variables y. Okay, because we have a specific value for each discrete random variable y sub j. So given that so by definition, this is just a conditional probability of Okay. And this probability, we can have A1 in capital A1, little A2 in capital A2, little AN in capital AN, probability X1 in A1, okay, divide by okay. Any questions? Okay. So the sum is by the countable activity of the probability function P. Okay. So this is from countable activity. Now, and so this is summation. Okay, and so this is conditional joint PMF. Okay. Okay, so that this conditional probabilities we discussed in chapter 3. Of course, that these events are related to discrete random variable x sub i's and y sub j's. Okay, they are described by discrete random variables. All right, and so that this condition probabilities actually can be computed from the conditional joint PMF of the x random variables given specific value for y random variables. Okay, so we have that. Okay, and in particular, the conditional joint cumulative distribution function of x1, x2, up to xn, given that y1 equal to d to y1, y2 equal to d to y2, that ym equal to d to ym is defined as the probability that x1 is less than equal to d to x1, and random variable x2 is less than equal to d to x2, is up to random variable x sub n less than equal to d to x sub n. Okay, given given that for all x1, x2 up to xn in R. Okay, so we now state the generalization of proposition 6.4.A and 6.4.B. Okay. Now, the joint PMF of m plus m discrete random variables x1, x2, has the following identity. Oh, not P, PMF, sorry. M, okay, which is equal to the conditional joint PMF of x random variables given the y random variables has respective values times the marginal joint PMF of y random variables. Okay, and also equal to if we exchange the rows of y's and the x. Okay, so this is for all. All right, so these two identities are true for all m plus m variables. Okay, and the identity is exact. Okay, and also an extension of 6.4.B is this statement. Two collections x1, x2, 2xn, and y1, y2 up to ym of discrete random variables are independent if and only if the conditional joint PMF of x random variable given y random variables Okay, so we regard this as a function with n plus m variables is equal to the unconditional joint P&F of x variables for all x1 Okay, so we have this statement here. Okay, so let's take a break up to 2:30. Okay, so the next section, we will discuss condition distributions on jointly absolutely continuous random variables. And okay, so for simplicity, we consider two jointly absolutely continuous random variables x and y with a joint PDF f of xy. Okay, so that we know at the beginning that two random variables x and y are jointly absolutely continuous. And we are given a joint PDF f of xy. Okay. It has been shown in chapter 5 that x and y are absolutely continuous individually, so that they are absolutely continuous random variables with PDFs. Okay. And f sub yy. Okay, with PDFs respectively. And we know which are computed from the joint PDF f of xy. Okay, so this is the data, okay, at the beginning. This is what we know from chapter 5. Now we define a new concept. So we define a conditional probability density function of x given that y is equal to y as, okay? So this event occurs with zero probability, right? Because each x and y, right, is absolutely continuous. So they are continuous random variable. So as a conditional random variable, an event like this has zero probability. Okay. So even this event occurs with probability, but we now define this object, even though we call the following function as conditional probability density function of x given this information. Okay, we can still define it. Okay, so this function is just by definition. It's defined to be the ratio of if it's positive. Okay? So if the denominator is positive, okay, then the conditional PDF of x given y, okay, is defined. And it will define to be the unconditional PMF if equal to 0. Okay, so in terms of the density, so even though this event occurred with 0 probability, but the density function of random variable y at little y could be positive or 0. Okay, this is the reason why we are able to define a function like this. So at this moment, you can see the definition of conditional probability density function has a nature which is quite different from the conditional probability mass function of a discrete random variable, given another discrete random variable has a specific value. Because in the previous sections, the concept of conditional probability mass function is actually a special application of the conditional probabilities of an event given another event in chapter 3, as you already know here. Okay, but for the absolute continued case, you can see that even though the name of conditional probability density function we also say given that y equal to y, but the nature you can see that's is quite different. Okay, quite different. It depends on the marginal probability density function. Okay, not depends on the PMF of y. Okay, because the PMF of y is the all-zero function. Okay, it contains no information. Okay, so for absolutely continuous cases, that information is contained in the probability density functions. Okay, as we have experienced in chapter 5. Okay, in chapter 5, as well as when we discuss independence. Okay, independence between random variables in section 6.2. Okay, so that's okay. So the definition, you can see that they follow similar patterns, but the nature will be different. All right, for the absolute continuous case from the discrete case. Now, here we make several remarks. Okay. The conditional PDF of a random variable x given another random variable y, okay, has a specific value. X a non-negative and integrable functions of x in R for each y in R. Okay, so for each given y, fixed y in R, then you know this is actually so that the integration over x, okay, in the whole real line is equal to 1. And third one, the conditional PDF over x given that y equal to y defined in the above has the same have the properties of a PDF of an absolute continuous random variables. Okay. Now the motivation. Now we check out motivation. For such a definition of conditional PDF is here. So we assume that the joint PDF f of xy is continuous on R square. All right, in this case, and then the two marginal PDFs, f sub x of x and f sub y of y. All right, so when the integrand is a continuous function, on R square, then these two functions, okay, are also continuous. On R. All right, and we assume that the joint PDF is continuous, and we assume that the PDF of y is positive. Okay. So now consider the following conditional probability. Okay, so we see the following conditional probability. The X is in a bin. Okay, so the bin is a very small interval of length delta 1 with a center at x. Given that the y is in another bin, okay, with a center at little y. Okay. And this is quite critical, right? Because for any measurement devices, it has precision. Okay, it has precision. So you can only say that the value of a continuous random variable is in a certain bin, right? And the size of the bin could be very, very small. It depends on the precision of the computer you use. Even you use the supercomputer, it still has a precision. Okay, so that this is the condition probability that you can ask for. Okay, so if you want to answer and to compute such a conditional probability, this is a conditional probability we discussed in chapter 3. Okay, the difference is that now these two events are described by random variables. Okay? So by the definition, this is actually the x is in this bin and the y is in this being divided by probability okay. All right. So now, by the definition of joint probability density function, we know that this is equal to okay. So this is the double integral of the joint PDF, okay, over the Cartesian product of this interval with this interval. And the denominator would be okay. So this is this one. All right, and this, if the delta 1 and delta 2 quite small, by the assumption of continuity, all right, so that this is actually equal to, all right, so the numerator is the, we find the representative point x and y times the area of these two, of this Cartesian product. Okay, so this delta 1, delta 2, and this one would be delta 2 here. And when delta 1, delta 2 is small enough, then actually this is very close to the number. And by our definition, this is actually is this conditional PDF of x given y times delta 1. Okay. Okay. So that for all 0, okay, so we have that. Okay. And in fact, all right. So in fact, that as limit divided by delta 1 is going to equal to f. Okay, so we have that. Okay. So this motivate that the definition of conditional PDF is meaningful, okay, in answering questions about conditional probabilities between events defined by x and another event by y. Okay. All right, so here is the, so for any Borel set, and the full discussion about conditional probabilities will be given in chapter 7. Okay, so chapter 6 is a preparation. Okay, we prepare for the discussion with more insight in chapter 7. Okay. So for any Borel set A in R, so we define, okay, so we define the conditional probability of the event X in A, given that Y has the specific value Y as, okay. So this must be defined. Why? Because this event occurs with zero probability. So that if we look at it as a conventional conditional probabilities, then of course this is by definition this is just an unconditional probability of x equal in A. Okay, but in here, more specific, in the case that x and y are jointly absolutely continuous, then this we call the conditional probability of the event given that were defined to be okay, the integration of the conditional PDF of x, all right, given y equal to y over the Borel set A. Okay, you have to know that the conditional PDF has the properties of the PDF of an absolute continuous random variable. So this is just by definition. Okay, this is just by definition there. So you have quotient here. I think I have to quotient. All right. So even though this is probability. All right, so that this is a conflict, a little bit conflict about the notation we used. Okay, so I ask you special quotients that the conditional probability of this event given here. It's defined in this way: if x and y are jointly absolutely continuous. Okay, but it is clear that if the probability density function of random variable y is 0 at the d to y, then by definition, Okay? In this case, the conditional PDF of x given y is equal to the unconditional PDF. And in this case, we have that. Okay? So this is good when what? When the PDF of this absolute continuous random value capital Y has zero value at the little y. Okay. So this is the quotient you have to know. Okay? And in particular, the conditional cumulative distribution function f of x given that it y is defined as the conditional probability that the event that random variable x is less than or equal to little x. Okay, so that this is equal to okay. So this is so that we have. So these are all new concepts. Now with newly defined conditional PDFs, we want to know its relationship with the original joint PDF of x and y. So let x and y be two jointly absolutely continuous random variables with a joint PDF f of x, y. Then, for each y in R, f of x, y, okay, is equal to the conditional PDF of capital X given capital Y has a specific value little y times the margin of f. This is just for almost all x in R. Okay, where the marginal PDF of x is computed from the joint PDF of x and y. Okay. The meaning of is that the length of the set such that is equal to 0. Okay, so we show the proof. We give the proof here. So this is for each y. Okay. So now we separate the proof into two parts. For y in R, such that the PDF of y at little y is positive. So we have that okay for all x in R. Okay, and so this implies that okay for all x in R. Okay, so for y in R such that the PDF has positive value, then the identity actually is true exactly for all x in R. But for y in R such that fy, which means that it's 0. Okay. So that the integral over x is 0 in this case. So we have that f of xy is 0 for almost all x in R. Okay. Right? Because the integral is non-negative and you integrate over the whole interval is 0, which means that the length, so which this is saying that the length of the set such that is 0. Okay? Okay, so that f of xy is 0 is equal to times 0, okay, and is equal to because f sub y of y is 0 here. Okay, so they are equal for almost all x in R. Okay, because here, the first equality is true for almost all x in R. Okay. Okay. All right, so we give the proof. Yeah. So the worst case, even though for rows y such that f sub y of y is positive, this is true for all x in R. But when, in this case, the identity only true for almost all x only. Okay, so, right. So we take the weakest one, the weaker one, right? With the weaker one says that the identity is true for almost all x in R. Okay. there is some remark which is quite useful. Proposition 6.5.8, which is the previous proposition, implies that the joint PDF of x and y is equal to the product of the conditional PDF of x given y times the marginal PDF of y, right, for almost all points x, y in R square. Okay. So this is a further or weaker expression. Okay, so we regard this joint PDF as a function of two variables x and y. Then this function is equal to the product, and so this product is also a function of x and y, but they are equal for almost all points in the plane. So this, which means that the area of the set is such that of this set. This is a subset in R2, right? And in R2 we measure the area. This area is equal to 0. Now we write down a proposition showing that how to compute the conditional probability of an event described by X given another event described by B. Okay, so if X and Y are two jointly absolutely continuous random variables with a joint PDF f of xy, then for any two Borel sets A and B in R, we have now, so the joint probability that random variable x has value in A, random variable y has value in B. Okay, so this joint probability can be computed by the conditional probability of the event at x in A, given that the random variable y has a specific value y, and weighted by the PDF of y and by. Okay, so we can compute the joint probability in terms of the condition probability of the event given the information of y, specific information y. Okay, and then weighted by the probability density function of random variable y. Yeah. Okay, and the proof is quite simple. Quite simple. So by the definition of this conditional probability, so we have that okay, so this is actually y in B, x in A. Okay? Right, so this, by definition, I think we give here. So this is the iterative, right? It's an iterative integration. All right, and we move everything here. Right, now, this one, because this is equal to by this proposition, this product is equal to this one for almost all x in R, so that we can replace. So over integration over x, we can replace this by the joint PDF. So this is by proposition 6.5.8. Okay, and so this is the double integral. Okay, this is double integral here, so that this is the probability of the random vector is in this Cartesian product. Okay, and this is equal to x in A, y in B. Okay, as we wish. Okay. Okay. So this shows that the definition here, this definition is quite useful. Okay, and this definition is in terms of the conditional PDF of x given random variable y has a specific value little y. Okay, so the joint probability. Okay. So in many situations, if we want to find, so in particular, so you can see here an application is that if we want to find a probability of the event defined by x, then we find another information, y. Okay, so y is a side information. Okay, so this comes to be okay. So you can see that you just integrate over all y in R, right? And in many situations, it is quite easy to know this conditional probability from the problem itself. So you need only to find the PDF of y, and you do this integration. So you can find this one. So this is the way to find this probability indirect. Because a direct evaluation would be very sometimes it's quite difficult. Okay? Sometimes it's quite difficult. And so this is another way around. Okay, another way around to do it. Okay, so I stop here and I will continue to deal with the absolute continuous case in the coming Thursday. Okay, so once again, please know that we will have a midterm examination next Thursday. Okay, so see you on Thursday.